Hello there. Welcome to our today's science lesson. The topic for the day being thinking scientifically. Now today's topic is just a continuation and an enhancement of all the previous topics we have been doing. It's just some kind of an addition, and in fact, after looking at how to think scientifically, we will also go through some one or two questions pertaining the previous areas we covered as we conclude the unit. Now, just to look at the previous work done so that we can connect it to our today's work. In our previous lessons, we looked at the various labs, and in those labs, we looked at what we normally find in those labs, and we narrowed down to a chemistry lab. Having looked at the chemistry lab, we looked at the apparatus, and we looked at the main source of energy being the Bunsen burner, where we had to test and see which type of flame is supposed to be used and is commonly used in the lab. We went further to look at how to write a report. Remember, whenever you are doing something in the lab or scientifically doing something, you are supposed to communicate. And in the sense of communication, you have to communicate it in a proper manner such that whoever you are interested in to receive the information or to continue with the same information should not be in any way confused. So we looked at how to write a scientific report. After that, we looked at how now to set up your own experiment. You need to write a report of what you have set out to be in a proper manner. So we looked at how one can set up his or her own experiment. But now, how will you look at that experiment and conclude that this experiment is worthy being done? How would you be writing that report? How would you be doing all the readings so that you can do proper recording as you are writing the report? There is only one thing you are supposed to do. You have to think scientifically. This shows that science and maybe other areas of study are a little bit different. The way you will orientate your brain, the way you will perceive issues in science will be in a way different from the way you will be perceiving either different or similar issues when you are undergoing other forms of studies that are not scientific. So let's look at how you are supposed to think scientifically. Now, in thinking scientifically, you always have to question everything. Thinking scientifically, always question everything. Why? This is because in most cases, there is nothing that happens just for the sake of happening. When it happens, the way it has happened, something was behind it. It doesn't just happen that way. So, in showing that this is how to think scientifically, we have to look at a situation that happens. Then from that, it ignites you on how to think in a particular manner. I will want us to personify some animals here, and the animal we want to look at is a bear. Imagine a family of bears, but in this family we have three members. The members are the father, the mother, and the child or a baby. So we have a father bear, a mother bear, and a baby bear. These animals like taking porridge as their main source of food. They had prepared the porridge, leave it to be ready for them when they come back from a journey they just feast on their porridge and feel happy, only to find that their porridge had been taken. And probably, when you look at the father bears, mother bears, and baby bears' bowel, the contents are not to the same level. They have been emptied, yes, but not to the same level. At least you will have to question. It couldn't have happened that maybe the baby bear's porridge was taken in excess or was so sweet than the mother's or the father's for it to be taken in more amount, or maybe the father's was more sweet to be taken in more amount and the other one was not sweet to be taken in less amount. We must have one or two or three or so many factors that could have been considered by whoever did whatever was done for that individual to take either more of the baby's porridge or mother's porridge or father's porridge. In doing this, as you are reasoning out to understand what happened, you have to look at some of the things we mentioned in the previous lessons, like variations. You look at variations, because if you are looking at the baby's porridge, look at the container into which maybe the porridge was kept. Look at the mothers, look at the fathers. If you are to study to understand the fathers, you have to make the mother and the baby constant. What are you looking at? These are variables. So as we said earlier in the previous lesson, when looking at any study that has more than one variable, and of which we always have more than one variable, always keep the other variables constant. Always keep the other variables constant. What we normally call constant variables. Then study one particular variable. But remember, we also have independent variables. So the two I've mentioned are dependent variables. And in these dependent variables, you keep all the others constant as you only work with the one dependent variable. And if there is any independent variable, then you also put into consideration and know how to use it. So I would like us to look at this data, which is also a representation of what we learned earlier, that for us to understand the data, for us to record data, there's a better way or a good way of doing it, and that is using a table. And each table must have a proper heading. As you can see, this is a table, and the table has 4 headings. The first heading is to do with the time, and this time we are going to work with a unit by the name minutes. Remember, I said that whenever you are using any item to do with the measurement, then make sure the units are well shown. That is already a step to show that you are thinking scientifically. Make sure all the units have their, all the aspects have their units, so that you can be able to explain quantitatively or qualitatively. We have temperature of Papa Bear's porridge, temperature of Mama, that is still Bear's porridge, then temperature of baby, still we are talking about the Bear's porridge. So let's get the figures, and from these figures we shall be able to discuss, analyze, interpret. And how to interpret? We require things like graphs. So let's look at the data first. We shall talk about 0 to 5 minutes. So we have 0 time, 1, 2, 3, 4, and 5 minutes. So this is the time we are going to use or to take for us to understand whatever happened. So that is the table. Now, checking on the temperatures, remember this temperature is also a unit. We have to know into which units are we going to read the temperature. So it is supposed to be in degrees centigrade. So this one is also degrees centigrade. Remember, it is also bears porridge, units, degrees centigrade. So we discover at 0 degrees centigrade, the father bear's porridge was at 60 degrees centigrade. You look at the mother bear's porridge, that is at 0 degrees centigrade, it was at 58 degrees centigrade, and the baby porridge was at 61 degrees centigrade. Now, this is the initial temperature. It is the initial temperature of this porridge. One can easily wonder, why don't we just talk about a common temperature? Remember, when you are preparing that porridge, maybe the father is prepared differently, mother differently, baby differently. You don't expect, even if they are from that sufuria or container for preparation, will be at the same temperature. They will vary in a little way. And as you can see, 60, 58, and 61, they are very close to each other. But what is important is what happens. As you cool. That is, as the temperature goes, they will be cooling. So after 1 minute, the porridge for father bears was 55. Then for mother is 48. The baby is 50. Now looking at it, already there is something you can decode out of it. Look at the drop in the temperatures. What is the drop here? 5 degrees. The drop here, 10 degrees. And the drop there is 11 degrees. So it's like one is cooling much faster than the other. What are we going to look at? Already a mind of variables start coming in. As you have just partially developed the table, but from that partial development, an ignition in your brain comes in. What could be the aspect? Already you are interpreting roughly the data. And as you are interpreting, you should already be trying to figure out what could be the reasons why this is happening. Look at maybe the porridge. Was it more thick? Was it light? Is it the color of the porridge? Is it the container? That is how to think scientifically. Think outside the box, as they always say, not inside the box. Imagine of all the possible things that cannot even be linked, but you think can be linked in a one way or another. Obviously, as you continue reasoning out, you will either qualify or disqualify your statements. Then looking at the second minute. Let's skip. Maybe we don't record the temperature at the second minute. There's a reason why I will wish we skip for the father bear's porridge at the second minute. This is to assist us get it later when we shall be using other modes of presenting data, like the graph. Can you use that graph to get this figure? Remember what we did in the previous lesson? We had such a similar case. So this one is a kind of a summary as I began when the lesson was on, by saying that this is a kind of a review of what we learned. Mother bears has a temperature of 39. Then the baby is 48. Third minute, we have father 45. Then mother 31. 31, it looks like 7. 31. Then baby 30. Fourth minute, we have father 40, mother, let's skip that one so that we can get it from the graph. Then baby 20, and lastly father 35, mother 18, and the baby 10 degrees centigrade. What are you seeing in the table? There is what we can call a trend. We can easily pinpoint a trend. And the trend is all the cases we are seeing the temperature reduce. It is dropping. The second trend is the cooling rate of the father bear's porridge is slower, and seemingly that of the baby is faster, because look at where it began, 61, and where is it after the 5th minute? It is at 10. From 58, 18. From 60, 35. So this one is cooling very fast, and this one is the slowest. As a scientist who is thinking scientifically, as I've said, as you go on with the data, you should be getting out some reasons to explain the variations, whatever you are seeing. And this comes in by you identifying what we call variables. Now, having gotten the table, let's look at questions. Remember, in science, whenever you are doing an experiment, always design questions. Always design questions. And it is from your answering of the questions that you achieve the target you wanted in getting or explaining whatever you are working on. So for us to be able to explain this, it will be good enough for us to design some questions, and out of the questions we shall answer the questions with respect to these data. So question number one is identify which bowel cooled the fastest. So we are talking about bowels, and out of these 3 bowels, bowel for the father, the mother, and the baby, having all cooled, these bowels, we have to identify which one cooled the fastest. Which one cooled the fastest? Is it babas, mamas, babies? Or there is also a possibility of saying the information I'm having is not enough to answer the question, which is always very true when it comes to science. You may be given data, then be given a question, and you are asked, use the data to answer the question. If the data is not enough to give you a justifiable answer to the question, don't force it. What you state is the data or the information is not enough to assist me, to help me, to make me answer the question. So what next? You will have now to design another experiment. Remember what we said on what you are supposed to do as you design your own experiment. So you will have to redesign that experiment or another experiment so that it can suit the objective of answering that particular question. So the question is, can we get the fastest, the bowel that cooled the fastest from this data? Is it possible? Is it possible? For me, I think the data is enough. And yes, it is enough. We can see from 60 to 35, we have 60 minus 35. The drop in temperature is how much? What is the drop in temperature? You always have to do the calculation. If you are not so sure, you use a calculator. So the drop here will be 25 degrees centigrade. So the drop from original to final is 25 for the father. The mother, we have 58 minus 18, and that is, we have 40 degrees centigrade. And for the baby is 61 minus 10, and we are having 51 degrees centigrade. Now, whether you use this method or this one is just the same, I've shown the two so that you can get that they are all the same. You will still get the answer you want. So we are seeing the change here to be 25, 40, and 51. They are all coming from these values, final these ones, but the time is the same. So being that we have kept a variable by the name time constant, we can now look at the variable by the name temperature. We have kept time constant. We now look at a variation to do with the temperature. If time is just 1 minute, then all of them. Or if it is to look at all the minutes, if time is 5 minutes, what was the temperature? And if this is the temperature, what will be the change? The change. The change is coming from constant time, or this is a variable, but variables to do with the temperature. And the difference is that. So it gives us the baby's porridge to be the answer to that question. Another question. This one is to present the data in a different format, and that is using a graph. So I want to sketch a graph, and out of that graph, we see how you can link the graph with the data and identify which one is for which. Remember, sometimes the table may not be that good, but if you present it in a graph form, it becomes even much better. So let's see using a sketched one. I have a graph, and this graph, remember, we say that it must have labels. So we have temperature, that is in degrees centigrade, against time, which is in minutes. That labeling is very important and show that the graph can continue to various points. Then, remember, it's a sketch, it's not a plot. So from my sketch, I want us to see if we can be able to link whatever I've sketched to whatever we have. So I can have one that is running this way. I labeled it as A. Then I can have another one. I label it as B. I can label this one as C, and I can have this one. Sorry for the shakiness of the hand, but assume there are all straight lines. So we are having 4 straight lines, A, B, C, and D. Out of all these 4, I don't know, maybe they have a representative or they don't have. I want us to confirm together. Could we be having any of these that could be representing the data of any of these 3? The father, the mother, and the baby. Let's look at number 1, or A. There is a starting point is high, but looking at the end point is low, but not that low. Look at this difference. If you are to extrapolate this one, it will come to somewhere here. So it's like the drop in temperature is so small. The drop in temperature is so small. So I don't know, in your own view, if A could be presenting any information from this table. Let's leave it at that point. Let's look at B. Now B is starting from slightly higher than A and C, but a significant drop to this. So at least is reasonable, but not very low. Could it be standing in for any data along these three? You decide. Let's look at C. C is starting the lowest, but also looking at the drop, it is dropping much lower than B. Could it be standing in for any? You will state it. Then lastly D. D has ended the lowest and seemingly it started the highest. So showing that it has the biggest temperature change. Now, if this was a plotted graph, is a confirmed graph, is a good graph, which of these lines, the 4 lines, represent these 3 sets of data? Have a look at it again. I think D will be standing in for our baby's porridge. Why? Because we got the highest temperature change at this point, 61 minus 10, we got 51. And looking at it, D has begun from this point, the highest, and it has gone to the lowest. So it has to give us the highest temperature change. So D is for the baby. So this one is the baby. Then look at C. It started the lowest, but looking at also the terminal point, it is the second lowest. Looking at the starting point, 58 is the lowest. So it qualifies. So C becomes the mama. We have the mama bear there. Then looking at A, we automatically see that it doesn't suit anyone because the drop is very, very small. It is almost like it is straight line, although a small inclination, which doesn't qualify here. We had a difference of 25 degrees centigrade here, which is reasonable enough because it is almost to a half. So if you look at B, where it began at second highest. Here is B, second highest, which is 60, second to 61. So at that point and ending at B, I think this one qualifies to be the papa's bear porridge. What are we getting from this? We are doing what we call relating information. That is how to think scientifically. Be able to relate information and single out the correct or the wrong. If you cannot be able to relate this to this, if you are just roughly given any data, then know that you are not thinking scientifically. Always know how to match. Always know how to synchronize informations. Can be in terms of diagram, can be in terms of data, can be in terms of graphs, but always know how to link. Then from this linkage, we can easily say that A has been singled out not to be in any of the data we have here. Again, from this, if it was a plotted graph, you can now easily come in and be able to fill in our question mark points where we were missing our temperatures. So if this is temperature, you know the highest at this point The highest at this point was 61. This one is 60. We have this one is 58, and so on. And you can see the lowest somewhere here is 10. From this, just identify the time. The time is 2 minutes. You are interested in the father bears porridge. So at the second minute, where you also have here 0, then 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5. Just identify at the second one. You know which graph is standing in for the father. So that is second minute. It takes me to the father. Remember, this is the father line, that's B. Then from there, follow horizontally to the y-axis. This is the point. The figure you get here will be the temperature you are supposed to feel at that point. What does it show? Scientifically, as you are thinking scientifically, be able to fill in missing gaps. Remember, whenever you are doing an experiment, there is one way or another where you can skip or be unable to get some figures or data. Probably you made a wrong reading. You made a wrong reading at this point. And you didn't want to crucify yourself in a way, if I can be allowed to use that, crucifying yourself with that wrong figure. So what do? Continue with the experiment, because it is important that you complete the experiment. You continue with the experiment, but from the continuation of the experiment, you will be able, using the graph, to get now the figure, since this is a line of best fit after plotting. And you will have saved yourself a great deal. Probably you had gotten a figure here of, let's say, 52, and you really feel, no, this one cannot do. Don't stick on a figure that you feel you already know is wrong, since you are always supposed to be sincere with your recording. So we are through that, and probably by virtue of the trend here, I guess it was something around 50 degrees centigrade. I'm not saying that it is 50, but going by the trend, it was likely to be 50 degrees centigrade. Now looking at the mothers, that is at which minute? The 4th minute. So with the 4th minute, identify the graph for the mother, that is C. 4th minute, good. We go, there we are. Then from there, let's go and cross the y-axis. There we are. That is the temperature you are supposed to get at this point. If you were not so sure of what you got, now from this one, you will perfectly be comfortable with the figure. And even if you present to somebody, will say you are very serious with what you are doing. I think that's enough for that. Let's look at another question. Maybe it can be helpful in a way. Now, the other question is, identify which of the following variables are unlikely to have much effect on the cooling of the porridge. Remember, in experiments, we talk about variables. And always look at one variable, dependent variable, that is, at a time. So the question is asking, of the variables I want to read out, which one is most unlikely, not likely, unlikely to affect the cooling of the porridge? Number 1, size of bowel. That's a variable. Size of bowel. So you can carry out an experiment, have a particular size of the bowel. It can be maybe this shape. It can be this shape. It can be that shape. Any shape. And any size. So this one is small, this is big, maybe this is bigger, and all that. So can such affect the cooling rate of the porridge. Another one is amount of porridge. Amount of porridge. Now, if you are looking at amount of porridge, you have to make sure that you look at the shape and the size of the bowel to be constant. For the size of the bowel, make sure the volume is the same. So you can vary the size of the bowel, but the volume of the porridge is constant. Now, for the second one, we are talking about the volume or the amount of the porridge. If you are varying the amount of the porridge, make sure the size and shape of the bowel remains constant. So, can it work? Let's keep it at that. Number 3, amount of sugar in porridge. Amount of sugar in porridge. Can it be of any effect? Remember, sugar is an impurity in that porridge. The porridge was maybe made of flour. So when you add in that sugar, you are kind of adding in an impurity in that porridge. Will that impurity affect the cooling rate of that porridge? Let's wait and see. Number 4, starting temperature of porridge. Starting temperature of porridge. We have 60, 58 and 61. Do those 3 temperatures affect the rate at which porridge is cooled? Look at them again. Take a few seconds. I'm sure you can agree with me that irrespective of the temperature where the cooling starts, it cannot affect the rate of cooling. You can see this one began at 61, but it ended up being the first one to cool. This one was the lowest to start, but you can see 18 and 10. 10 is even much cooled than 18. So the starting point of the porridge, the starting point of cooling of the porridge does not matter. So we have already singled out D as a condition that most unlikely to affect the cooling rate of that porridge. Now, maybe to revisit the first 3, we have looked at the size of the bowel. If the size of the bowel is to be looked at, the others must be constant. Now, if it is so big, if the bowel is big, and then we have a small one. When it is big, the porridge will be exposed to a bigger surface of the atmosphere. Because of that, it will be steaming out, which means heat energy is going into the environment. In so doing, it makes the porridge to cool faster. So bigger bowel will make the porridge to cool faster. But small ones, very little surface will be exposed to the atmosphere. Because of that, the steaming out will be to a smaller extent. And as a result, the cooling rate of the porridge in a smaller bowel will be slower than the cooling rate of porridge in a bigger bowel. So at least you should have learned something from there. If you will be the one now to take porridge one day, or you take that coffee of yours or drinking chocolate of yours, and you really want to get it very fast, you are late to school, then think of a bigger cup or a bigger or a wider container for it to cool faster. The second one was the amount of porridge. The amount of porridge, that is an obvious case such that the bigger or the more the volume of the porridge, the slower it will be cooling. Because as the upper surface is cooling, do you think the inner ones will still be cooling at the same rate as the outer one? Obviously not. So you'll find that by the time you have the upper part cool, so that we can also affect the lower one to cool, it will take longer if the volume was so big. But if it is so small, then it will easily cool even the inner ones, and you find that with the smaller volumes, then you will get the porridge cooling faster. This one is also seen, for example, if you are taking that coffee of yours, if you take a small amount in that mug or cup, and maybe your father, mother, friend, whoever has a similar one, but has filled the cup or the mug, do you think the coffee will be cooled at the same rate for you to take very fast so that maybe you can run to class? The answer is no. The cooling of the small amount will be faster than the cooling of the large amount. And lastly, the amount of sugar in the porridge. The amount of sugar, as I've said, is an impurity. So if these three porridges are in different containers that are the same volume, so which means we are putting volume and the container, that's the bowl, constant as a variable, but now a dependent variable that is kept constant. We only vary the amount of sugar crystals. Then you will discover that the one that will have a higher amount of sugar, remember it's an impurity, and impurities affect cooling or boiling or heating, for that matter, of substances. Then the one that will have more crystals of sugar will cool at a slower rate, because impurities also retain heat energy. So you will have to release the energy from the porridge, at the same time release the energy from the sugar crystals. So the more the sugar crystals, the slower you will have to cool, because it will have the so many crystals to lose the energy, the heat energy, before it cools. Then one last question pertaining the same, that is in respect to this, that's why I didn't erase that Baba Bears forgot to read his thermometer, and at once identify the most likely missing temperature. Identify the most likely missing temperature. As you can see at this point, second minute, this for the bears experiment, the mother was doing hers, the baby doing hers, and the father also doing his. And at this second minute, it forgot. So we have been given figures. What could be the most likely temperature that was missed at this point? I had already said 50, but now I don't know. Let's look at the figures first. So the figures are 31, 53, 50, and 18. 31, 53, 50, and 18. Out of the four sets of figures, which one do you think is most likely to be the missing figure? And I think from already what I had said, the answer will be 50. But you don't just say 50. Scientifically, you always have to state a reason behind everything you give. That is what we call thinking scientifically. There is always a reason behind everything. Nothing happens for the sake of happening. So, if you have picked on 50, why do you think it is 50? And the answer is, there are two answers. One, depending on the graph you plotted, you went for the further graph, then you came to the y-intercept, which is temperature, and you got at this point, probably it is 50 degrees centigrade. So you can say from the plotted graph of the father bear's cooling graph, the point of intercept where the second minute has been used on the graph, the temperature is 50 degrees centigrade. Well explained. You will have stated where you are getting the fact and what you did on that graph for you to get that particular point. You identified the graph, it is the father bear's graph. Which graph? The cooling rate of porridge. At what time? At the second minute. Then you looked at the intercept, which was coming from the 50 degrees centigrade. The other way you can also look at it is, now that one is not very recommended, but is a faster way of trying to pinpoint before you now come to conclude the way you have done it. And that is, you now go in for speculation. You speculate. You are kind of extrapolating information, going by the trend you are reading from the table. So as you can see, from 60 to 35 is like a drop every after 1 minute is a drop of 5 degrees centigrade. Because of that, you can comfortably say, since this was 55 first minute, then highly likely the next temperature will be 50 degrees centigrade. But remember, that is not the best. The best is get it from a graph. So that marks the end of our interpretation of the data we had been given. And from this, I think you have seen how one is supposed to look at issues scientifically. Because for you to be a scientist, there's a special way of looking at every issue. And in every issue, always look for a meaning, look for a cause, look for a reason why it is happening the way it has happened. Now, when I was starting the lesson, I mentioned something to do with linking what we have just been doing with what we did in our previous lessons, as we shall be summarizing the unit, because this will be marking the end of the unit as we prepare to handling another unit. Now, in this unit, we have been looking at aspects of how to communicate. We have looked at the lab, which is the special room for scientists. And finally, we looked at how to try to set out your own experiment so that you can write that scientific report. But in qualifying everything, you have to set your mind or your brain to think scientifically what you have just been looking at today. But even as you have seen it, that thinking scientifically is just similar to what we did previously. So it was like another set of experiment just to emphasize on what we did previously. Remember the issue of the beverages. So I would want us to go through the previous cases we did using questions and see how much you can remember and how accurate are you in remembering those aspects. I will start off by looking at units. I start off by looking at units because I remember having said that in all measurements you do in the lab, make sure you include units, and not just units, but correct units. So let's look at this question. State two metric units commonly used. State two metric units commonly used. So we have commonly used for at least something. Remember, commonly used, yes, but where? So we have one commonly used for, number one, in distance. If you want to look at distance, that is the measurement of length. Which common units, metric units, can you find somebody using? So in distance, we have several, but the common ones are millimeters. Remember, in the chemistry lab, our apparatus are not so big. The apparatus are not so big, so the common unit you will always see will be millimeters. Then we also have centimeters. So these are the common metric units, though we also have the meters, but these are the common ones we use, particularly in chemistry lab. Then we also have volume. We have volume. common metric units we use in measurement of volume. We have the milliliters, which I also said that milliliters is the same as cubic centimeter. So when you find somebody using cubic centimeters and another one using milliliters, the two are talking the same language. Then we have liters. Again, liters, you will find other people using decimeter cubed. So when you find somebody using a liter and another one talking about decimeter cubed, then the story is the same. And lastly, mass. Mass, you want to measure mass in the lab. You have been told to take this mass, add into this and see how it reacts. How do you get the mass? The common ones we use is grams. Then we have also the kilograms. But remember, we also have tons. But I doubt if we can be, in a way, it can be possible for us in the lab to use tons. We commonly go for grams and kilograms. But remember, since you are a scientist and you go to high-tech labs where very high-level research are being done, they can go as low as milligrams. Milligrams can also be used. Like when you are talking about a lab that is being used to analyze athletes before participating in, for example, world marathon and such, to avoid doping. In doping, you are talking about very small amounts of banned substances in your body, which will not come in terms of grams. They will come in very small amounts. So in such, you would be going in for milligrams and such. So that is our first question, which has seen us through the units one is supposed to use. Now the other one is second question. This to do with the safety. Remember, in the lab, safety is important. And this takes us to our second question. Describe the features of a safety flame. Features. You describe the features of a safety flame. So we want to look at a flame in the lab. Not just anywhere, but we are talking about a flame in the lab. But not just a flame in the lab. This flame has to give us safety. Safety in the lab. So we want to look at a flame. But this flame should not just be any other flame, but a flame in the lab. Then that flame in the lab must guarantee us safety. So the first thing we have to look at is which type of flames do we have in this lab? And there are two. We have what we call luminous and non-luminous flame. So we have luminous and non-luminous flame. So out of this, we have to pick out a flame that is associated with the safety, and that is luminous flame. So this is the flame associated with the safety in the lab. Now, from that, let's now look at the features. Features of that flame that qualifies that flame to be called a safe flame in the lab. Number one is visibility. It is visible. It is visible. It is yellow in color. This other one is blue in color, but that color, since the flame, since yellow and blue, yellow produces a lot of light, then it makes it even more visible. Then there is the size. Luminous is large in size, while non-luminous is smaller in size. So you can easily pinpoint out these by size. Then we can also look at the amount of heat energy produced. So it produces less heat energy. It produces less heat energy, such that if accidentally you get in touch with the flame, I'm sure you will not complain so much as compared to the burn you will get when you are in touch with the non-luminous flame. So these are the three main ones. These are the three main ones that you can comfortably bang on to say this is the flame I'm to always put my Bunsen burner in for me to be safe in the lab. Another question to do with the safety. A question to do with the safety. I'm interested in the safety because no good experiment will be called good if the one carrying out the experiment end up dying because of an accident. So the other question is, explain why the senses of taste and smell are rarely used in science. The senses of taste and smell, senses of taste and smell. These two senses, remember we have 5 senses, but we can talk about the sense of eye, the sense of touch, the sense of hearing. Those ones are used. I can see that this is a blue, this is a yellow. That is the sense of seeing. You can use the sense of touch. When those bowels were cooling, you can easily touch maybe the outer surface of the bowel and say, oh, the baby's bowel looks to be more cold at the end of 5 minutes than the father's bowel at the end of 5 minutes. Sense of touch. You can also use the ears, that in this reaction there is a sound being produced, but in that other reaction no sound is being produced, what we call a favor sense. So at least you can use those ones. But we rarely use the sense of taste and the sense of smell. That is using your tongue and using your nose. Why? Because these are 2 tastes that can interfere with your body physiological process. When you are tasting using your tongue, probably whatever you are tasting is poisonous. I'm sure you are not safe, because it will obviously go into your body and it will poison your body. And the same happens to smelling, because when you smell, if it's a gas, it will go into your lungs. If it's an acidic gas or basic gas, it will easily collapse your lungs. So that's why we rarely use these 2 types of tests, just for your own safety. Lastly, let's look at a question to do with the graphs. Let's look at a question to do with the graphs, and also something to do with the report writing, scientific report writing, which will be summarizing or finishing off our lesson today. Because remember, those are the last aspects we were looking at. So in report writing and also in graphs, there is an aspect of reading that is very important. Reading. So there is what we call meniscus. Define the following terms. Let's define the following terms and try to explain them. Define and try to explain the terms. So number 1 is meniscus. Number 1 is meniscus. So when it comes to reading volumes, containers, any container you'll be using for volume, if I can use a measuring cylinder, it will have calibrations. So when you have a liquid in it, the upper part will be seen to be curving. the upper part will be seen to be curving, as you can see that. That is what we call the meniscus. So the meniscus is the curved upper surface of any liquid when in a narrow container. You cannot see this like in a lake. That's a very wide surface having a liquid. Or in a very big basin, you cannot see that. But in a narrow container, that curvature on the surface of a liquid in a narrow container is what we call meniscus. But it will be very useless for us to mention this and we don't know how to read it. So how to read meniscus is identify the lowest point of the meniscus. And this should be done by an eye point at 90 degrees on that apparatus. So that is how to read the meniscus so that you can do proper recording. The second one is cross-section. Cross-section. Now this comes in when you are talking about a graph. You have drawn a graph and you want to interpret the graph. Though much of this is seen in mathematics, I'm sure you must have covered in mathematics a great deal. Now when it comes to cross-section, it is important for you to know the interpretation on the margins, that's the y-axis and the x-axis, because it is out of the point of meeting of these crossing points that you will be getting either the answer on the x-axis or the y-axis. So we normally use dotted lines for you to get to particular points that you want. So please know how to get the figures on the x-axis, know how to get the figures on the y-axis and in the correct units. So the most important thing here is labeling of the axis and the units. Then on finding the point of interest, use dotted lines. Then second last is hypothesis. Hypothesis. When we were talking about writing scientific report, I remember having mentioned the hypothesis as an educated guess. You guess, but in a more educated way, that this experiment I'm doing, I guess if this happens, this will happen. Remember, at the end of it all, it doesn't have to be right. But I doubt if you are a scientist and you force yourself to guess wrongly, you will guess at least towards the direction you want. So this is just an educated guess that whatever I'm doing is likely to give me this kind of results. Remember the issue of the tennis balls, that the height of the dropping ball will give me or will be directly related to the bouncing height. So the higher I go, the higher the bouncing the ball will do. That was a hypothesis. You go in, do the experiment now to qualify the hypothesis. And lastly, we talk about variables. The variable is the last thing we have talked about and is the most important thing in science. In doing an experiment, always look for the variables. Identify all the variables. Then from there, state questions attached to the variable. And now, what's a variable? A variable is just an aspect that will give different results when another variable is changed. That variable can be dependent or independent. But since it can be varied, if you vary that one, then it makes this other one to vary. Just to remind you, you can talk about a variable like temperature, which was depending on an independent variable, which was time. So the longer the time, the more the temperature was dropping. Temperature was depending on time. that marks the end of our lesson today and the end of the unit we have been covering for now. Till next time, thank you.